equals sine x minus cosine x, cross the x-axis, anywhere between 0 and 3 pi over 4. And let's just do this, pardon me, let's do this the old school way. Let's take sine x minus cosine x and see, is it ever 0 between those values of the angle? So we have sine x minus cosine x equals 0. The easiest way to deal with this, or at least one way to deal with this, is to move something to the other side so that we can examine both functions. So can we easily move cosine?
Yeah, just by hand.
So we have sine x equals cosine x. Now, let's take a look at, where are we? We start in the first quadrant at 0 radians. Where is 3 pi over 4? Second quadrant, good. Both functions have what sign in the first quadrant?
We'll close it up. I'll leave it first.
Good. And in the second quadrant, what are the signs?
Negative, positive.
Okay, good. So if we need these two functions to be the same, we must look in the first quadrant. In the first quadrant, is there anywhere that we know that the sine and cosine have the same value? Yes, pi over 4. Good. We know that the cosine of pi over 4 is 1 over square root of 2, and that the sine of pi over 4 is 1 over square root of 2. This is a 2. We will very rarely rationalize. Very rarely will we get rid of square roots in the denominator. Trig functions are all about symmetry, reciprocals. Anything we can do to keep this simple looking will help us become enlightened when we manipulate it. So it appears that we start at 0 and go up to pi over 4. And then start at pi over 4 and go up to 3 pi over 4. Can we just leave the dx off? It doesn't really do anything, does it? That's a trick question. What does dx tell us?
We're taking the remainder.
It's part of the operator, and it tells us that the variable is x. And it's necessary. Okay. I had I guess a pre-cal student the other day say, oh, can't we just leave the pi off? There's so many. No.
It's Thanksgiving.
So, we don't know if we're looking for, I guess I already erased it, if we're looking for the net area or if we're looking for the actual area, the displacement. So we're going to find these integrals separately. Hey, bud. Joey's daughter's sick.
Yes, he's up
Okay, but wait, there's more. He, asked me if I would ask you if you could take notes for him. Oh, you already took that one. Good. So first let's find sine x minus cosine x. If we're looking at just the part below the x-axis, excuse me. And we already said that we know of an antiderivative of little f of x. We said that f of x, capital F of x, equals negative cosine x minus sine x is an antiderivative of little f of x. And that means by the fundamental theorem of calculus part 2 that we have f of pi over 4 minus f of 0. Let's see, what is f of pi over 4? What is the value of cosine of pi over 4? And I really am going to encourage you to write the unrationalized version of this. It's 1 over the square root of 2, and the negative is from the formula. And then what about the sign? Groovy. And adding, we get negative 2 over the square root of 2. And this is the first time we have a hint that maybe we can simplify this. Let's come over here. Negative 2 over the square root of 2. I don't know if I can make it simpler, but let's see. What can I multiply square root of 2 by to make it not a square root? Good. So in the numerator is negative 2 root 2, and in the denominator, groovy, and now what happens? That's the only time we're going to rationalize, when it actually simplifies an answer. And remember, we said that this part of the area was negative. It's below the x-axis. And it is indeed negative, and that's nice. So now, if we're starting at pi over 4 and going to 3 pi over 4, get the same situation. Oh, we didn't finish. My bad. I apologize. We needed to see what f of 0 is. The other limit. So negative, what is the cotangent, cosine of 0?
1.
Yes, and the negative in front makes it negative 1. And the sine of 0? Good. So we have negative root 2 minus -1. And if you want, we can put the 1 in front. 1 minus root 2. Is this still a negative number? Which is larger, 1 or the square root of 2? That's right. Square root of 2 is a number between 2 and 3, between 1 and 2, and so it's bigger than 1. So we do indeed get our negative area, and let's do the same thing for here. We'll have f of pi over 4 again. We said f of pi over 4 was negative square root of 2, and we need to find f of 3 pi over 4. So we have negative cosine 3 pi over 4 minus the sine of 3 pi over 4. We're in which quadrant? Remind me? We're 3 pi over 4. Second quadrant, good. So what SIG in? What is it, plus or minus for the cosine in quadrant 2? Good. So this negative sign is from out front. But I know that inside here I have 1 over root 2. And then another negative from inside. Is sign positive or negative in quadrant 2?
Positive.
Good. So we have negative, negative. So we've got positive 1 over square root of 2 minus 1 over square root of 2. And what do we get?
0.
So the entire area between pi over 4 and 3 pi over 4 is 0 minus negative root 2, so we get positive root 2. Now, we have a value for this first bit. We said that this is equal to 1 minus root 2, and we have a value for the second bit. So this is square root of 2. How do I find the net change?
By adding them.
Just add it, that's right. And we have 1 minus square root of 2 plus square root of 2, and we end up with 1. So the net change is 1. What do we do differently in order to find, they're both areas, but the actual displacement, the area? What do I do? I've got the value of the first integral and of the second.
The absolute value. of
Good.
the area.
So we have the absolute value of 1 minus root 2 plus the absolute value of root 2. And y'all already told me that root 2 is larger. That means that the absolute value of 1 minus root 2 is root 2 minus 1. the larger number changes sign, the smaller number changes. Now, we have root 2 minus 1 plus root 2, which gives us a kind of weird looking answer. 2 root 2 minus 1. But do you understand that some applications will want that, and some applications will want just a net change? Okay, great. Why don't y'all let this old woman sit down, and y'all all work together, everybody work together to make noise. I heard from all of the other students in our class, they're all having issues. So,